Greetings. This is the project presentation of Group WG11 on video streaming with RTSP and RTP under the guidance of Professor Kalyan Sashidhar. The team members are Nilav Shah, Harsh Patel, Dakshveer Singh, and Japan Bhatt. The objective of this network application development project was to develop a client application and a concurrent server application using RTP RTSP protocol that provides video streaming service to the user. The project task involved understanding the RTP RTSP protocol's functioning and implementing the actions that are taken when buttons are pressed. RTP class to packetize the video data and calculating the statistics of the video stream. The video streaming server plays an integral part in the project by serving requests made by the client. The following are a few important characteristics of the RTSP RTP server. The server can handle requests from multiple clients at the same time. The server maintains session of each client for the provision of RTSP commands like setup, play, pause, and teardown. The server also synchronizes frames and their corresponding rate of transfer appropriately. This is the block diagram of the server implementation. The server is started, it creates a socket, it binds itself, and it's listened to the socket. When a client connects to it, it accepts, and a client thread is created. As part of the server implementation, the next big thing is to handle client requests individually in a thread. The following are the steps involved according to the flow diagram description. A. Initially, the thread will be waiting for the setup request from the client after accepting the connection. Next, on receiving a client request for it for setup, it creates a UDP socket for further communication or sending the video data. On a play request, the thread will start sending the video packets at corresponding frame rates using another thread. At last, the thread iterates back to listening for any further future request from the client to handle functions like pause, teardown, and etc. This is the client implementation block diagram. The client raises a series of RTSP message requests to the server to establish a RTSP session and which are followed by play, pause, and teardown events. This is a demonstration of how the packetization is done. Uh, this is the header of every RTP packet. It is a 12 byte packet. Now let's look at the first byte of the packet. It contains version, padding, extension, and CC number. These all parameters are given to us in the encode function as parameters. Now we need to, by applying bit shifting logic, we have to encode this byte data. So here is the demonstration for the first byte. The header 0 represents the first byte of the packet. Version is a 2-bit data. So it is shifted 6-bit to the left by the left shift operator. Then its logic ended by number C0, which is a 8-bit number having all bits unset except the 7th and the 8th bit. Then next, after this, padding is bitwise odd with the previous header by shifting it to the left 5 bits. Then it is followed by the extension number, and we shift extension number 4 bits to the left. And at last, we add the 4-bit CC number, which is bitwise ANDed with 0f, which is equivalent to first, second, third, and fourth bit of the data set. In similar logic fashion, all of the data is packetized. This is the state diagram of the server. The server can exist in three states: init, ready, and playing. Whereas the client can send four types of request. The setup request causes the server to allocate resources for a stream and starts an RTSP session. The play request starts the data transmission on a stream allocated via the setup. The pause request temporarily halts a stream without freeing the server's resources. And at last, the teardown request frees the resources associated with the stream and the RTSP session ceases to exist on the server. Now, initially, the RTSP state is set to init. When a setup request is received by the server, it changes its states to ready if the call succeeds. Now, the RTSP state must be ready as a prerequisite for the play button, which starts the video streaming. The RTSP frame sequence is then increased and the RTSP play request message is sent to the server. The response of the server is parsed and the RTSP state is then set to playing if the streaming has begun successfully. Also, the timer is started for the current session. While the stream is active, the RTSP state is playing. A pause request would send a temporarily halt request message to the server in order to pause the video streaming. Upon the receiving the pause request, the server response is passed and the RTSP state is reverted back to ready. Thus, timer is halted to continue at a later stage based on the client request to resuming the streaming. The teardown button is similar to the pause button, except that it requests the server to end the current streaming session completely. Hence, the RTSP state is reverted to init and the timer for the current session is stopped. Here is the logic implementation of a request transition. This is for a play request. So here, this handler assumes that the prerequisite that the server is in ready state. Also, it increments the frame sequence and the response of the server is parsed and the RTSP state is set to playing. This is part of the optional assignment one, which is calculation of statistics of the streaming. For here we have calculated three parameters, which is frame lost rate, the data streaming rate, and the total number of bytes streamed, for which we have to initialize some extra variables in the client class. In the constructor method of the client class, we initialize some variables which are cumulative lost, the last high sequence number, the total play time, the total number of bytes streamed, the data rate, the fraction lost, and the cumulative lost. These are initialized in the constructor method. Another variable, self.start time, is initialized in the play movie button, which is handler of the play button. It uses the Python time function to calculate the stat start time. Also, in the send RTSP request method, we calculate the number of packets accepted by subtracting last high sequence number from the current frame number. We also calculate the numbers of packet losts by subtracting last cumulative lost from the cumulative lost. And later we update the last high sequence number by current frame number and the last cumulative lost as the cumulative lost. We then use these methods to carry out further calculations. The first code block shown is of the listen RTP request, which is running as a thread of the play button. Upon receiving a data packet, we calculate its arrival time by the same methods used in the previous slide. We calculate the current time, and then we subtract the starting time from the current time, which is then added to the total play time. Also, then we update the start time as the current time. Then we use the methods provided by the RTP packet class to calculate the current frame number and get the payload. Then we calculate the length of the payload and store it in a variable. All these calculations done and the variable used are later used in order to update the labels. So the data rate uh, is indicated by a ternary statement here. If the For the initialization, if the total play time is 0, the data rate is sent to 0. Otherwise, it is calculated by dividing the total number of bytes streamed by the total play time. Also, fractional packets loss is calculated by dividing cumulative loss dividing by by current frame number. Also, we update the total bytes by adding the current length of the payload. This all calculation is done and the packets are updated in the GUI. So the handler updates the time of the streaming. It extracts the payload data and other information such as the frame sequence index, the payload type, timestamp, etc. from the received UDP packet. It also checks if the packet received is latest and updates the statistics like a missed packet, total packet count, total streaming time, and streaming rate. Finally, it displays them as labels in the GUI. Now moving on to the presentation. For starting the server, we run it by this command python server.py, and we pass the parameter the port number of the server. Now in the another terminal for the client, we run the command python client launcher.py. The first parameter of this is the server name. You can name it anything here, it is redundant. The next parameter is the port number of the server, which is same as the previous one. The next parameter is the client port number, which is this. And the last parameter is the name of the file, which is movie.mjpeg. This brings up the client prompt. When we press setup, we see down here that setup request is sent by the client, and also a setup request is processed by the server. Now we can play the video. As you can see here that the total byte received are incrementing. Also we can see the data transfer rate here. Since this is very optimized, there are no packets being lost. We can also pause the stream, which sets the data transfer rate to 0, and also the byte streaming halts. We can again play it, and anywhere in between we can tear down the connection. So here we see a teardown request was sent by the client. Sorry, it is processed by the server, and in this prompt a teardown request was sent. And we see the current sequence number are the number of the frames which are being processed. So in this file approximately 500 frames are there. Now since our server is concurrent, we can connect multiple clients to it at the same time. So I open up this command prompt for the first client, and I Run the same command for another client here, and I change the port number for the second client. So we see that two clients are generated. For each one we can set up, but both of these can stream data independently. You can play at different time, pause them if needed. Also, since we are recording it, this is a little bit slow, but when no recording is done, the data streaming rate goes very high. When multiple clients are running in parallel, the data rates drop significantly. We can pause this one, pause this one, create this one, create this one. So after receiving around 500 frames, I guess both of the files will stop. So this was the demonstration of project done by group WG11. Thank you.